So, all right. So, yeah, thanks, Tuzer, for the great talk. So, go back to this picture. Now that we know how to learn this kind of general visual representation from different type of learning methodologies like supervised learning, like masking. Sorry. Oh, sorry. Yeah. Yeah, great. Okay. So, yeah. So go back to this picture. So now that we already know, okay, how we should learn the image representations from different type of learning method, like mask modeling, like supervised learning, like contrast learning, etc. So in this talk, I will try to answer the second question, that is how we should turn the vision models to more generic, flexible, and prompt one. In other words, how we should build a general purpose vision system on top of the foundation model to address a wide range of vision tasks. So talking about the general purpose system, it's natural for us to revisit on how language models evolved in the past years. I guess we all know and hear about the GPT and the ChatGPT and amazed by ChatGPT, right? So if we take a look at the NLP domain at the very beginning, different tasks actually are coupled with different models. So at that time, actually, we can use different kind of sophisticated design architecture with maybe LSTM, maybe RN, or even CN to cope with different tasks. But gradually, thanks to the image of the transformer architecture, the building block to different NLP tasks are converging to decode-only architecture, aka GPT service, for example, GPT-3. And later on, the GPT models learned through simply predicting next token is further instructional tuned to support human AI interactions. Then ChatGPT comes, which changed not only the research community, but also the society fundamentally. So, and this only takes 4 years from 2018 to 2022. It's very short, right? So this will motivate us as a computer vision researchers to think about, so what we should do for vision. So if we do a similar projection for vision, now we are coping with different types of tasks for image level task, like image classification, image captioning, and the region level task of detection, grounding, and the pixel level task, segmentation, reference segmentation, depth estimation, etc. So actually, we are curious about how we can follow a similar path like the language model to first do the unification, and second, empower a human AI interaction for computer vision model. However, we cannot easily copy-paste the technique from NLP to computer vision. As we all know, computer vision tasks actually are very diverse and fragmented, which renders several challenges to build and the so-called generalist vision models. I will summarize a little bit. So first, the vision task actually need to cope with different type of input. It can be static image, it can be temporal image, it can be single modality, only just RGB pixels, it can be probably a combination of multiple modality, for example, vision and language. And second, there are different granularity of tasks. For example, we have image level tasks like classification, captioning, as I just mentioned, and also region level tasks, and even the pixel level tasks like segmentation, super resolution, etc. So moreover, the output, unlike large language model, are also of different formats, containing spatial information like age, box, mask, or semantic information like class level, multi-level text, or even descriptions, or very dense descriptions, right? So all of these kind of challenges actually make it very hard for us to think about the very simple way to do the unification of different computer vision tasks. In addition to the challenge on modeling part, actually, there are also challenges on data. First, due to the different cost to enter the different type of data, by natural, we see a pyramid of scale. From the bottom to top, there are image annotations, box annotations, and mask annotations. And the semantics start from rich to poor, from bottom to top, while the granularity starts from the coarse grain to the fine grain. Second, it is much harder to collect the image data compared with the language data. So the scale of the vision data is much smaller than the language data. So this is another challenge we are facing in computer vision in terms of the data scale. So despite such kind of challenges, so as a computer vision researchers, as a community, actually we are trying to develop some kind of general purpose vision. So this is our aspiration, right? So first, there are some efforts to turn this kind of closed set classification into open word recognition. As Sir showed in his slides, the contrast language image model like CLIP has empowered immersive zero-shot transferability for image classification. And second, we are trying to convert the specialist model to generalist model. For example, at the beginning, actually, we developed different type of models for different tasks. For example, for fast sensing for detection, mass sensing for segmentation, and a bunch of different kind of visual question answering models. But now we are seeing more and more kind of generalist model, the so-called generalist model, like pixel to sequence, like unified I/O, like XDecoder. All of these models had attempted to generalize and build some kind of generalist model to unify all of the tasks. Of course, it's just an attempt. And so instead of merely learning visual representations, like their BIP, like Dino, like MAE, introduced by there. Actually, recently more and more people are focused on how we can build a promptable kind of system or interface beyond this kind of representation learning. So at the very beginning, actually, we are talking about, when we talk about the foundation model, we are mainly talking about the representation learning in terms of foundation. But now, actually, the times has changed. So we are more talking about, okay, whether we can train some kind of foundation model that can support end-to-end task without any fine-tuning. So this is basically the trend and the attempt in the computer vision community. And this trend, I would like to highlight the three words: open word, generalist, and interface. These three words together exhibit a great aspiration for the computer vision people towards the next generation vision understanding system. In the next, I will try to walk you through the detailed techniques behind each of their components. First one is So for the open word, we need to bridge the vision and the language. The intuition is very simple, right? The language as a common space is a common space to share information across many people, right? And the benefit of this is that, okay, we can effortlessly do the zero-shot transfer from one task to another one. And the second is the unification of different granularity. And the intuition is also very simple. So computer vision is tackling different tasks and different granularity. So we are expecting whether we can build some kind of unification model to unify different granularities to enable a cross-task synergy. For example, different tasks maybe have different kind of semantic information, have different granularity. So whether this kind of cross-task unification can help to enable some kind of cross interaction across different tasks. And for the interface, actually, we should enable the system to support and take various prompts as input. But this kind of prompt should be different from the language model. So in the vision, actually, it's not necessarily a text as prompt. We can probably also draw a box. We can also draw a point, a stroke, or even a hand gesture, etc. That being said, actually, this prompt should be much more diverse compared with the language model. And the benefit is also very simple. In this way, we can reduce the ambiguity of expressing human intent. So we can use the language as a message, as a bridge to share the information. And we can also use some other type of kind of prompt to let the model understand the user's intent. For example, a stroke. So let's first delve into how we should bridge the vision and the language. So in the past years, a number of works have attempted to bridge vision and language for visual understanding at a different granularity. If you look at this two-dimensional axis, the x-axis is granularity from the image level to region level to pixel level. And the y-axis is the semantics from just a simple label, 1, 2, 3, 4, just simply a scalar label to the language labels, the semantic concept. So if you look at this figure, in the past, we have already seen a lot of effort to convert or transform this kind of regular classification task or region level classification task into this kind of recognition task. But saying that, recognition means that you need to map the visual content to the semantics, not just a discrete label. So there are two observations behind this kind of figure. So most of this method actually follow a similar kind of trend to build a bridge by converting the labels to language, because most of them probably are inspired by the clip, I would say. And the second point is that it turns out this coarse-grained knowledge can be transferred to fine-grained tasks, which has been already proved in many previous work, like the GLIP or many other kind of works in the object detection domain. So most basically, put these two paradigms side by side. You can see on the left side actually is a regular or classical image classification model. And you can see actually to classify a visual content, we just encoded the labels. So this label does not contain explicit semantics. But on the right side, actually, if I compare them, it's pretty simple and straightforward. You can see, okay, we are replacing the label embedding with some concept names, with some kind of semantic meanings, and use text encoder to encode word concept as their language tokens. So by this way, actually, we are projecting one of the visual content which can be described semantically to a semantic space, which is commonly shared by one of the tasks. So in the following, I will explain specifically how the reason works bridge the vision and language for pixel level task. Because in the last year, we already talked a lot about how we can bridge the vision and the language for image level task, for region level task. But here I will refresh you with some kind of new works talking about the pixel level tasks. So image segmentation requires a model to group pixels with similar semantics. The task can be further categorized to generic segmentation, like semantic, instance, panel segmentation, or reference segmentation, given a text as input, and we want to segment specifically a region from the image, from the audio. So the methodology actually can be categorized from different aspects. First, so whether it should be initialized from clip, or we can train from scratch by combining a lot of image text pairs. Second, whether we train the model using VP supervised training or a supervised training. And third, whether we are using a two-stage model, like first a mask proposal and then a classification, or an end-to-end training. So below, I list some kind of recent work that are related to this topic. I will just pick a few of them for the interest of time. So one of the first work I would like to mention is a group VIT. So it's trying to learn to group semantic similar regions by learning from image text pairs from scratch. And it's exploit a bottom-up grouping using novel grouping block as shown here. And it will further exploit a top-down image text supervision for the visual semantic alignment as shown in the middle figure. And finally, it turns out that, okay, it works pretty well to emerge some kind of grouped region, which becomes a mask, a semantic mask for the given image. So unlike the group VIT, the mask clip actually use the clip as a teacher and attempt to extract the free label from the clip. After a bit tweak on the output layer, the model actually by itself can predict meaningful semantic mask as shown on the left side. So the original kind of clip model actually used the left side kind of attention-based pooling. I guess most of you already know that. And on the right side, actually, it's abandoned this kind of P and Q projection and directly use the value function and plus the linear layer to get the output. And finally, you can see some hidden map, which are highly overlapped and aligned with kind of semantic informations. So then, based on this kind of free supervision extraction, the user further explore this kind of pseudo label kind of mask to further train some segmentation model, which is called mask clip plus. And it turns out that this mask clip already works pretty well to extract the semantic mask from the image by only leverage the clip without any further training. But if we further train the model with some pseudo label data, actually the mask clip plus will significantly improve the performance of the semantic segmentation. So you can see here, this makes a lot of difference from the figure C and figure D. So the mask clip and the mask clip by using the specially designed kind of adaptation. So differ from the previous two works, OpenSig is another work, and it uses weak supervision from image text pairs and mask information from segmentation data. So by mask segmentation, mask annotation means that, okay, it does not use any label data associated with a mask. It's just use a mask to train a model to propose the mask proposals, and that's it. And based on this mask proposal, it will do very simple kind of mask-based pooling to pull the feature extracted from the clip or elan vision encoder. And finally, it will do some kind of fine-grained alignment between the text tokens from the left side and the regional or mask-based pooled tokens from the right side. And it turns out that even though it's just weakly supervised by image text files, actually it will learn to segment the image very well, as you can see from this column. And afterwards, if the author further add some kind of local narration, which means that, okay, it has some kind of more fine-grained kind of alignment between the text and the image, then it will further improve performance, even though this kind of local narration developed by Google actually is still very nice, not golden annotations at all. So another mask clip, also called mask clip, and a lot of work called mask clip. And this one from UCSD actually explored supervision, supervised training for panoramic segmentation. And it used a clip as well, but use it as initialization of the train and train the model on COCO. Similar to OpenSig, it also pre-trained a class agnostic mask proposal network and then adapt the pre-trained clip model and a new model called RAM to finally align this kind of mask code feature and the textual invariance. So it turns out that we can see from this reading that, okay, the clip baseline based on this strategy does not work very bad, right? So, and after use this kind of master proposal, you can see it slightly improved the performance compared with the clip baseline, which means that, okay, so if we really want to do a very good kind of open archive segmentation, the spatial information is one side and the semantic information is another side. And based on this kind of pipeline, it will further train the model on top of the COCO panoramic segmentation data and adapt this kind of model on ADE and Pascal and to evaluate the different kind of segmentation tasks. You can see here this kind of supervised training, but in the vision semantic space will significantly improve the performance of the open archive segmentation. On the other hand, yeah, as you can see here, basically the library information significantly boost the performance, as I just mentioned. So putting all of the methods together, we can see that different methods use different pre-trained checkpoint or supervision to bridge the segmentation model with language. From the left side, actually, we can only use the image test paths without any specific kind of golden supervision or master supervision. And gradually, we can initialize the model with click pre-trained model, which already contain a lot of kind of semantics, even though the semantics actually is pretty coarse-grained, but it still can significantly improve the performance of the segmentation. And then, okay, we can better add some kind of a mask to train a mask proposal network to help to extract the fine-grained region for each of the object or the background stuffs. And later on, we can add labels associated with the mask and then jointly training both the segmentation mask proposal and also the segmentation classification. And you can see here the performance, the so-called open vocabulary performance can be further improved. And finally, I did not introduce this model, but XGcoder showed that, okay, what if we combine all of this kind of data? The clip model as a pre-trained initialization and the mask plus label from the COCO or from the other supervised data set and a rich image text paths together, just to put them together and jointly training on top of all of this data, it can further significantly improve the performance of the open archive segmentation. And compare group VIT with other methods. Actually, we can conclude that clip as a foundation indeed help a lot for open archive segmentation, even though the model was never trained for this kind of fine-grained pixel level alignment, but it still learned a lot of semantics alignment between the visual data and the text. And also comparing XDecoder with OpenSig and the other method, we can show that, okay, combining the image test files and the image label, segmentation label data together, it can further improve the performance. So this aligns with the previous observation for region level task. If we compare with for example, region clip and the clip, which did not use supervised training data, which does use the kind of supervised data and the image test pairs. So that's why I have covered some recent works that bridge vision and language for segmentation. And if you go back to this picture, you will see for all of these kind of core vision tasks, the image level task, the region level task, the pixel level task, actually we have been already successfully, maybe not fully successfully, but we already built a very great connection between the old-fashioned kind of classic computer vision classification recognition model to some kind of language interface to enable some kind of fancy or powerful zero-shot or open vocabulary capacity. Although this model are unleashed to recognize open world concept, but still mostly task specific, you can see here. So at each column, we are developing some model for classification, for detection, for segmentation, but it's not necessary that we have a single model to simultaneously do all of these tasks across different granularity. This really build, so to really build the generalist vision understanding model, we need to look at the task across different granularity, right? And connect them horizontally, not only the vertically. So this leads us to our next part on how to unify different granularity. And talking about different granularity, I would like to bring this figure back. But naturally, we are facing a data imbalance problem towards this goal because different kind of granularity of data actually contains different annotations. And as I mentioned before, the semantic information actually are different across different granularity, and also the spatial annotation are also at different levels. So ideally, we want to build a synergy across tasks of granularity. For example, cross-grained data should contribute to the fine-grained data or task with the rich semantics, because we can obtain a lot of image text files. And on the other hand, I think it's also very important if we can enable the model to share the knowledge from the fine-grained to coarse-grained to enable better grounding. So we want to build a synergy, but I'm not sure whether, okay, the following work exactly do what we want to do, but this is our final goal. So talking about this, let me have a quick recap on what kind of tasks we are usually considering, right? So image level, region level, and pixel level, I do not want to repeat it again. And in the next, I will talk about what's the most recent kind of unification methodologies. I categorize them into two types. One is output, the IO unification. So which means that it converts raw output into a sequence and develop a model to decode all of the outputs in a sequence format. And the second way is the so-called functionality unification. This kind of method actually share the comments maximally, but also with respect to the difference across different tasks. I will first talk about the high level kind of difference again with this kind of illustrative figure. You can see here on the left side, so the output unification is trying to decode the sequence for all of the task A to Z, and use some kind of task-specific decoder to decode this sequence out to finally produce the prediction for each of the tasks. But for the functionality unification, actually, we can see that the input may be not much different, but for the output, actually, it will produce different type of output, which are shared across different tasks. And then, okay, to finally produce the output, the model will combine different output together to finally convey the predictions. So with this distinction, let's first go through some methods that unify output with sequence. Inspired by language model, most of these methods actually converts their output either spatial or kind of semantics to a sequence. So for the semantics, actually, it's pretty straightforward, right? Language model has already done that. But for the spatial output like box, mask, key point, actually, some methods have already explored a very simple and heuristic way to tokenize this kind of coordinates to a sequence. For example, X, Y, and H and W, something like that for a box. And the polygon coordinate for a mask, etc. At least some of the most recent efforts to do the unification through this kind of output kind of way. So I will also pick some kind of method and talk about it. So the first type of work I would like to mention is a Unitab and the Pixel to sequence V2. This model unifies text and box in the same way without any specific model designs. They both use a common vocabulary, so they convert the text to the tokens in the vocabulary, and also combine the tokens from the special output like box, like polygon, etc., to the same kind of vocabulary. And on the other hand, actually, both of these methods actually will append a prefix, a task prefix, to tell the model what kind of task the model is going to tackling at this point. For example, you can see here, so for the Pixel 260V2, actually, it will append a segment and or keep on or describe this kind of task prefix to get the model to specifically decode some output sequence. And then the model will go back to check the output sequence and then use the task-specific decoder. This decoder may be trained or just a heuristic design. And when it goes to the pixel level task, actually, the previous two methods can hardly cope with this. So unified I/O is type of method that can further unify a wide range of understanding tasks, including segmentation. So to cope with this kind of pixel level or dense prediction task, the model will train the VQVE for each of the separate tasks. For example, for the mask segmentation task and for the depth estimation task, and one of these kind of tasks, the model will, the author will train some kind of task-specific VQVE. After they train the model, they can use the encoder, the VQVE encoder, to synchronize all of the input to a sequence and use encoder-decoder architecture, very normal encoder-decoder architecture. You can imagine it's probably T5, something like that. And to link this kind of mapping between the input sequence to the output sequence, and finally it will decode this output sequence to some real output, like the box, like the mask, like depth, etc. This is type of method can be further used to support the pixel level or dense prediction. Use a unification of the I/O manner. And on the other hand, actually, other works like Vision LM, it appeared actually last month, if I remember correctly. So this method further combine this vision encoder with some language encoder. This language encoder is different from the previous language encoder used in previous work. It's very large language model. So you can imagine it could be a llama, could it be OPT, could it be very advanced larger model. And it's plugged this larger model to help the whole system to decode the sequence. And this sequence will contain both the semantic information and the spatial information for the visual content. Indeed, it will unify a wide range of vision tasks so that the encoder-decoder can be trained end-to-end for different type of tasks and different type of input and output. And also, it also, in the meanwhile, it also requires a task-specific decoder to decode the sequence to find out. For example, it will extract the coordinate and translate it into a box, or convert the polygon coordinate into a mask, etc. And also use another VQV decoder to decode the hidden features, hidden feature map, or hidden sequence to a mask or to a depth map. And it might be hard to integrate the interaction across different tasks of different granularities, because you always see a sequence. You cannot understand exactly what kind of model, what kind of behavior the model is doing. And furthermore, it may not be able to build a strong cross-task synergy as we expect. So on the other hand, some other works actually is doing this kind of functionality unification. The intuition is very simple and straightforward. The vision tasks are not fully isolated, right? So for example, shared, a lot of tasks share the box output. The generic object detection, the phrase grounding, the regional caption, it's needed to predict some kind of box. And then this can be shared across different tasks. And the mask output can be also shared by instance, semantic, panoptic segmentation. All of these type of segmentation tasks actually can use a single mask decoder head to decode the mask. And also, of course, the reference segmentation, the example-based segmentation, etc. And for the semantic output, actually, it can be shared across different tasks like classification, image captioning, regional captioning, detection, segmentation, a lot of different tasks. That being said, okay, so what if we unify this kind of different tasks based on the categorization of the output? So you can imagine, you can see there are high-level two types of output. The first output is a special output. So either the box or the mask. And what's the second type of output is a semantic output. Is just described by, for example, through the language. So you can imagine, okay, what of these methods actually are trying to follow this kind of abstraction and unification in terms of the functionality. So I will also pick one or two to mention. So the first one is the Unification V2, and it's trying to unify classification, architecture, instance segmentation, image text retrieval, image captioning. Yeah, you can name it. A lot of different tasks, and basically it's exploit a unified decoder G, and this G will take different type of queries. It can be the queries from the detector for the detection. It can be the queries from maybe the segmentation or the captioning. So basically, you can imagine, so if we can build a unified decoder, and then this unified decoder can take different type of queries as input and decode a different type of output. And you can combine the output together to finally support different type of end tasks. And likewise, I would like to also mention the X decoder, the generalized decoding for pixel, image, and language. So this work is also exploiting a single unified encoder decoder architecture, which is called X decoder. And it takes two types of input, the latent queries and the text query. And it will produce two types of output, the semantic output and the spatial or pixel level output. And you can imagine by composing different type of input and output, it can support different tasks. And for all of these tasks, actually the model does not have separate kind of parameters. The parameters are fully shared across different tasks. It's just a routing for different tasks. Yeah. And based on this, for example, for the segmentation or for the generic segmentation, if we do, in this case, we do not have the text encoder, then we just use a latent query to ask the model to decode the mask for the whole image. And for the reference segmentation, then we feed some text embedding from text encoder to the X decoder, and then it will automatically understand what's the condition and then specifically segment the object. Likewise, for the image text retrieval, we do not need to produce a pixel level output. We just produce the semantic output and compare the similarity scores between the semantic output and the text embeddings. And finally, we can further do the image captioning and visual process answering by producing the output from the right side of the X decoder. Even though, okay, there is no other changes, it's just the selecting which part of the output to predict to make the predictions. So by saying this, actually, I briefly cover so how we unify the different granularity of tasks in the account stage. So it can be categorized in two different ways. The first is the I/O or output unification, and the second way is a functionality-based unification. And based on thus far, you can see, okay, we are doing some kind of unification, and also we are doing some kind of effort to trying to build a generalist model, which can generalize to new domains in terms of the vocabulary, in terms of the concept, and also it can be generalized to different types of tasks at a different granularity. So we are drawing these arrows vertically and horizontally. So it finally can cover different tasks in the computer vision. And by saying this, actually, I would like to also mention, okay, so there is also another workshop called Computer Vision in the Wild. It's happening now, and if you are interested to know more about what the effort towards next generation general purpose computer vision for classification, detection, segmentation, and beyond, yeah, please stop by this afternoon after you finish this tutorial. Yeah, and so the next part is about the promptable interface. So I will briefly walk you through the recent effort towards generalist vision and in terms of how we can build a promptable interface. So this actually is inspired and recently developed by ChatGPT and recently developed by several teams. So the motivation is pretty simple: how we can enable vision models to chat. So you can imagine if we only have the GPT, maybe it cannot be easily directly used to finish the daily task we have, for example, coding, writing an email, etc. But if we can do some kind of instruction following tuning and the human feedback in the loop, etc., we can finally build some kind of conversational AI like the ChatGPT developed by OpenAI. Likewise, given that we already have a generalist model, in the last slides we already draw the arrows vertically and horizontally. We already covered all of the tasks. Let's imagine, this generative vision model is perfect. Then what we can do to enable a good kind of interaction between the human and AI model. So in this, at this point, actually, we probably have two kind of ongoing efforts in the computer vision community. One is that, how we can develop a promptable interface for in-context learning, because this is indeed a very, very good property and the functionality showcased in the large language model. And the second part is that, how enable an interactive, multi-round interactive between the computer vision model and the human, so that it can help the human to finish complicated tasks and gradually refine the prediction results. So these two aspects actually have been recently explored to some extent. Of course, there are a lot of kind of open space. I will just briefly go through two works. For the first part, the in-context learning for vision. So this work is from Berkeley, and it's called visual prompting while image implanting. And it can candidate the in-context sample. You can see the first two. The task import example, just a regular RGB image, and then it will have the mask, and ask the model to predict a new mask for the query at the state column. And somehow, actually, the model works to some extent. And of course, it's not that good compared with segmentation model I showed earlier. For example, the OpenSig, the XDecoder, fireware, I would say, But this is a good effort to pursue this kind of in-context learning for computer vision. And another work is called SegGPT. Actually, it's appeared maybe 2 months ago. This is share a very similar spirit to the previous work. Given this kind of input image example, and also the model take a mask of that image and then give a new image. For example, give a new image like this, and then it will predict the mask for the Liberty statue's face. So this is basically pretty simple and straightforward, and it looks like we are somehow actually achieving the in-context learning for like the large language model, but I would say it's still far away because it's only cope with this kind of specific task like segmentation. But it's a good attempt. So beyond this kind of promptable interface for in-context learning, I'm sure you guys are very familiar with this work. It's enable an interactive interface for vision, which means that the model can support a multi-round of interaction between the human and the system. So this promptable segmentation can take different type of interaction mode. As I mentioned before, the computer vision task is different from the language model or language task in that it does not only take the language as input. It only takes some other kind of special interactions. For example, the point, the bounding box, and the stroke, the mask, etc. This kind of prompt is also very expressive to convey the information to the system. So you can imagine in the future we probably have a VR glass, and then it requires some kind of maybe interaction beyond the language as well. And based on this kind of promptable interface, they develop some very simple, straightforward encoder-decoder architecture. And based on this encoder-decoder architecture, it has run some kind of flywheel of the data to collect a lot of data. 11 million of images contain maybe over 1 billion masks, even though one of the masks are automatically annotated by the model. And finally, it trains some model to enable this kind of interactive segmentation. And this interactive segmentation are mainly achieved by deliver or feed the previous mask to this block, and then use a convolution network to encode the history mask, and finally gradually refine the mask given some kind of prompt or box-based prompt. And for SAM, actually, it's already has been widely used in different computer vision tasks. In this sense, actually, it can be called the foundation. So based on this kind of end-to-end segmentation model foundation, so a lot of people have explored different applications. For example, combine the segmentation model with impending to fill the mask region, or use a segmentation model to help to track the video object in a long video sequence. And then it can be further applied to the medical images across different types of tasks, including the segmentation and the detection. And again, so this kind of SAM is very powerful in terms of the promptable interaction. But as I mentioned, this SAM model actually only supports the spatial interaction. Prompt, box, it does not show a very, very good kind of capacity for the language or semantic prompting capacity. SIM is another work. It's called segmentation, everything, everywhere, all at once. And the reason why it's called like this is because, so the everything means the model can predict all of the labels, name all of the entities in the images. And everywhere means that, it can predict every pixel into a segmentation mask. Or advanced means that, it can combine different kind of prompts together by adding, for example, visual prompt plus text prompt, or reference prompt plus the text prompt or audio prompt, etc. So finally, you can imagine this model can do a very wide range of segmentation tasks. It can support in different type of prompting methodology or format. And it also supports a very good kind of interaction. So you can see there are some kind of examples. I will not explain it one by one. I just want to show, this is one of the example. Let's say we just draw a stroke, just a simple stroke on the first image. Then the model will use this as a reference prompt to segment all of the specifically specified object in the consequent frames. And even though there are a lot of kind of deformations, you can see here the fries from this image to this image, and also zoom in and blurring, etc. So this is pretty straightforward for you to use in a zero-shot manner, even though it's never trained to accomplish this task. So finally, I would like to have a quick recap on what I just discussed. So in this talk, I'm mainly talking about how we can achieve a very good kind of promptable and flexible and generic vision system interface. So it's more like an interface, it's not just a model. So to achieve this, so we first want to bridge the vision and language. I would say for this part, in the last 2 or 3 years since the clip, actually a lot of effort has been spent on this domain, and it has been successfully reshaped the researchers, computer vision researchers for classification, for detection, and for segmentation. Now we are not distinguish the vision language and the vision task anymore. And on the second point, we want to unify different granularities. So the different granularities, if we can unify different granularities, so the final goal is that whether, we can build a very good synergy across different tasks, because we do not want to unify this task for fun. So we want to build a coherent and a kind of flexible system to support different tasks. And finally, should take various prompts. And I would like to highlight here, for computer vision tasks, the prompt should not be only language prompt. It should be also contain some kind of special prompt so that it can be complementary to each other. And finally, can be the intent. So to the end, I would like to share this work conducted by our MS colleagues. And this work actually claimed that, they found some kind of sparks of AGI in the GPT-4. And indeed, there are some kind of sparks. So in the bottom, actually, you can see here, the model, even though without any kind of visual learning, can gradually learn to how to draw this kind of unicorn based on the tool called TIGZ. And you can imagine, so how capable it can do. And it was impressive to me as a computer vision researcher. So talking about AGI, I want to show you this figure. By natural, human brain has a lot of neurons which are responsible for different functionality and cooperate with each other to finish the complex task. It involves language, but not only language. It also involves the vision, the auditory sensation like speech, like audio, and also motor control. So in this sense, if we go back to our computer vision community, so it still have a long way to go, right? So we are trying to draw some dots between the loop, between the individual computer vision task and the unified generalist model, and then further, okay, build the connection between the unified model to the finally interactive and the promptable kind of interface. So you can see there are a lot of works are trying to pursue that, but it's still far away from the final goal we are imagining. So that's good, or that's bad, but also good because we are fortunate. All of us are fortunate to have a lot of kind of imagination to pursue this kind of generalist model for computer vision. So finally, I would like to mention that, okay, what we can do with this kind of generalist vision understanding model. So we can use it to enable a intimate cooperation with large model for physical world tasks. And finally, we want to give large model a very kind of precise eye. It's not just a broadly or coarse-grained eye. It should be a precise eye. And also we can further combine it with some kind of image or video generation or editing task, as well described by the next speakers. And so finally, so we want to achieve this kind of multi-sensory general intelligence that can see, talk, and act in both the digital world and the physical world. So this is basically a very, very great aspiration. But right now, actually, as a computer vision researcher, actually, we have a lot of space to explore towards this kind of generalist computer vision model for understanding. So that's it. So thanks for your attention.